Number one, today we're going to take a look at how we can apply a function to something we see in real life. Okay, so previously we learned that functions can be represented in multiple ways, like we saw in the first lesson. We can look at them as a mapping, like we see over here. We can look at it as a table. So if we were to organize all these values, what they're linked up with, into a table where we have x and then y, we saw sets of ordered pairs like we see right here. Graphs, once again, we put a plot of points on a graph, or sometimes they form a curve. We'll get into that later on this unit, next unit. Or we could write it as this new way of looking at it, where we have given a certain function, f of x, and it's equal to this. Find what happens when we replace x with -3. Okay, so those are all ways we can numerically look at functions. What about if we were to flip this on its head and look at it as, can I use functions to decipher and encrypt words? Well, we absolutely can. Concept of a function is applicable to something called cryptography, which is used in many different places, such as internet security, communication, computers, timestamping, and so much more. A lot of it deals with the security you have on your cell phones or even on your Chromebooks. Okay, so for instance, we're going to take a look at the communication side of everything. Okay, so we're going to look at communication and kind of mixing up words and how functions can be applicable there. Okay, so let's look at this example that we have on the next slide. Suppose a beginning cryptographer uses the mapping below to encrypt a message. Now, what's going on here? Once again, look at the first bubble. This would be considered our input. So if we put a word, any word we want to, in the input, this tells me, okay, I'm going to change an A to an X, an E to a T, an I to a Y, an O to a Z, and a U to a V. Whatever we do that. Everything else doesn't really matter. Okay, so if I look at the word cat, I look at what my input is. So once again, A, E, I, O, U. Obviously, my vowels, there's a vowel in cat. That means I'm going to encrypt the word cat to be C, and then A would turn into an X, and then we leave the T alone. So we would translate this to be CXT, or if we were to encrypt it that way. All right. What about algebra? Okay, so once again, how do we translate the word algebra using this key or this mapping? We look for our vowels. So A would be an X, so we'd write it as X, and then LG would be next. E would transform to a T, so XLGT, and then B, R, and then A once again changes to an X. So we'd write this as XLGT, B, R, X. Okay, so obviously it's a nonsense word, but if we're trying to keep our messages secret, then we'd be able to do it that way. What if we were to work backwards and translate the encrypted word STQVZYX using this key here? Okay, well, S is not in my range or my output, so we leave the S alone. T is there though, T becomes an E. And then Q is not there, so we leave Q alone. So far, first three letters are S, E, Q. And then V is in there, so V becomes a U. Z is in there, the next letter, so we work backwards to get O. Y is in there, so Y becomes I. And then X would be A, giving us the word sequoia, which is a tree that I believe is one of the biggest trees in the United States, at least in North America, but it's also a unique word because it uses all 5 vowels in one word. So kind of did that on purpose, So, all right, let's take a look at another mapping right here, very similar to the last one, but think about this in terms of input and output. Does this mapping represent a function? And in this case, take a look at what A does. A goes to both Z and X. And that's a problem based on what we know about functions, just simply because we know that for every input, there needs to be exactly and only one output. In this case, A gives us a little bit of a problem because if we try to translate something that has a Z or an X in it, we don't know which one we're looking at. So for instance, if we're looking at RZCK, we don't know if we're saying ROCK, because O goes to Z as well. But now that we've included the extra rule that Z would also correspond to A, we don't know if we're talking about rock or wreck, which is two completely different objects. Okay, so once again, a function needs to have that one-to-one relationship, otherwise things get confusing. All right. Another type of cipher is this one right here. They actually used this back in ancient Roman times, where we just kind of have we have a whole alphabet here, and then notice right here we have a little bit of a shift. All these letters in the second row are in alphabetical order. Obviously, when we get to Z, we restart, but it only goes ahead 3 letters, and then we restart after we get to Z. They actually used this to encrypt messages back in Roman times. Okay, does this table represent a function? Once again, as long as they have a one input to one output relationship, absolutely, this does represent a function. There's no confusion as to what something could be. And we're not going to translate this today, but I want to give you guys an idea. If we were given this statement right here. Obviously, in English, it's nonsense words. We don't know what it means. But if we were to translate it, we would kind of work backwards from it. So K would be, let's see here, H. H would give me an E. O would give me L. And then R is an O. So the first word we know out of this is going to be hello. Okay, if you want to translate that later, you absolutely may. But I just want to give you guys an idea of what that looks like. Okay. So now here's what I want you guys to do. Think about this for a second, okay? What similarities do you notice between cryptography and functions in algebra? Obviously, we've only dealt with numbers, but now we're going to take a look at it in terms of how we can use it to jumble up words. What are some differences you notice? What can we do with numbers that we can't do with words, and vice versa? What can we do with words that we can't do with numbers? All right? Your closing activity, which I've posted on your classroom page, is at this link right here. You're going to go to this website right here. And what I want you to do, there are 3 levels of 3 different types of encryptions that I want you to try and translate and decrypt if you can. And screenshot the highest one that you're able to solve and send it to me by 4 p.m. today. This will be your bell ringer or your exit slip for today, okay? And then if you haven't done it yet, make sure you finish all your Delta math activities for today. All right? Please message me if you have any questions. I'll see you guys later.